Welcome to today's session. As in previous sessions, we have gone through amplitude modulation. In today's session, we will see about angle modulation, where angle modulation is a combination of frequency modulation and phase modulation. Angle modulation is defined as a process where the angle of the carrier signal varies in accordance with the instantaneous value of modulating signal. For a signal, the angle can be varied by varying the frequency or a phase. So that's why angle modulation is again of two types, like frequency modulation and phase modulation. In today's session, we will see what is meant by frequency modulation. We can define our frequency modulation as the process of varying frequency of the carrier signal in accordance with the instantaneous values of the modulating signal. Actually, first of all, we will see a carrier signal. What is the relation between angle and frequency actually? First of all, consider one carrier signal, that is AC. We all know that carrier signal is represented by C of t. C of t, as we are taking it as cosine signal with an amplitude, frequency and phase. So we can represent our carrier signal C of t equals to AC cos omega ct plus phi, where here omega c is carrier frequency, phi is phase. Then now phi of t we can write it as omega ct plus phi. I'm taking another denotation like psi of t. If we derive this angle, frequency can be obtained and angle can be obtained if we integrate this particular phase frequency. So there is a relation between angle and frequency, that is by frequency modulation we can achieve phase modulation, by phase modulation we can achieve vice versa frequency modulation. That is the relation between frequency modulation and phase modulation. That's what here we are representing. Frequency can be obtained by derivating the angle modulation, and angle can be obtained by integrating the frequency. So simple, by using integrator and differentiators, we can able to obtain one from the other. So now in detail we will see about our frequency modulation, where the definition satisfies or not we will observe. What is the definition of frequency modulation? The frequency of the carrier signal, as here you can observe here in the waveform, this is message signal and this is carrier signal. As we know, message signal is a low frequency signal, carrier signal is a high frequency signal. Coming to definition here, the frequency of the carrier signal will be varied. This carrier signal will be varied with respect to instantaneous variation of the amplitude of modulating signal m of t. So for that purpose, if you observe here, for positive half cycle of input message signal, the frequency variation will be more, and for the negative half cycle of the input message signal, the frequency variation will be less. So that if you observe, this is the output of frequency modulation, that is modulated signal. So here this modulated signal represents where there is a frequency variation more, it is nothing but for positive half cycle, and for negative half cycle the frequency variation is less. So this is the modulated waveform of frequency modulation. Now we will see the equation of frequency modulation. For that equation, first consider the carrier signal AC cos omega ct. We all know that the frequency variation at the output is called as instantaneous variation. Yes, instantaneously it will be varied, right? So first I am representing that particular equation by the definition. See here, omega I. What is omega I? instantaneous variation of frequency. How the instantaneous variation of frequency is occurring? The carrier signal frequency is varied with respect to message signal m of t. So I can represent this omega I equals to carrier frequency, that is omega c plus, with some constant sensitivity factor kf into m of t. Where is m of t is message signal, kf is frequency sensitivity factor, which is measured in hertz per volts. Coming to the angle of the carrier signal after modulation, it is nothing but after modulation means there will be instantaneous variation of frequency. So phi of t, here we represented previously already, equals to integral of omega I dt. That equals to integral of omega I means just now we have given the equation omega c plus kf into m of t dt. So the same thing I am representing here. We are replacing omega I with the formula. Then now how much we will be getting? Omega ct is nothing but constant, so that I am taking it outside, and plus for 1 it is t, so that omega ct, integral of omega c, for 1 it is t, so omega ct plus kf integral of m of t. We all know m of t is our message signal. M of t represents message signal. So then the frequency modulated signal can be written as AC cos of omega ct plus kf integral of m of t dt. So this is the modulated equation of frequency modulation. From this, we can derive some of the terms like frequency deviation. Coming to frequency deviation, it is the variation of frequency we can represent. So the formula for frequency deviation is nothing but kf into m of t. Frequency deviation we can represent by using del omega. So del omega is nothing but kf into m of t. It is called as frequency deviation. Thank you for listening. In the next sessions, we will see more about frequency modulation.